Hey folks, got a little bonus video for you here, section 1.3. This is question number 10 in WebAssign. I've had several questions about this one, so I'm going to go ahead and do this one as an example for you to see it from start to finish. And the first student that asked me about it had the randomized numbers of -14 and 800. So if that happens to be the same as yours, great, you get a free solution. Otherwise, you're just going to have to follow along with my steps. Okay, so let's just read the problem first. Use the position function s of t equals -14t squared plus 800, which gives the height in feet of an object that has fallen for t seconds from a height of 800 feet on a particular planet. So for those of you that are going to be taking physics this year as well, these position function problems, we're going to be doing a lot of position, velocity, and time problems. And just so you know, s is often used as the variable for position. Okay, so that's the position function. It gives us the position in feet of an object that has fallen for t seconds. So think of it, it's like you're standing on an 800-foot tower and you've got a wrench or something, and I don't know why you would drop it, but let's say you just happen to drop it and that thing falls to the ground. This is the function that describes the position as it's falling. T equals 0 is from the start when it's 800 feet high, and then you drop it, and as time increases, the position decreases. Okay. They're also telling us that the velocity at time t equals a is given by the following, and it's a limit. So holy cow, it's the limit as t approaches a of s of a minus s of t over a minus t. So that's kind of crazy. This part of the problem is the one that many of you are kind of struggling with. So we'll get to that in a minute. All right, part A. If a construction worker drops a wrench, oh, that's why we had a wrench, because the construction worker had it. If he drops a wrench on this strange planet from 800 feet in the air, when will the wrench hit the ground? Round your answer to 2 decimal places. So the position function is given as this. Well, the position when it hits the ground is 0. It's 0 feet above the ground. So we want to know at what time we get that position of 0. So this is the equation that we're going to solve. We have 0 equals -14t squared plus 800. This one's a can of corn, folks. If you can't do this, then we need to talk. I'm going to move the 14t squared to the other side. Then I'm going to divide both sides by 14. And then I'm going to extract a square root. Now watch what I do here. I'm going to say, don't forget that when you take a square root is plus or minus square root. Now that's true if we're talking purely mathematical, but this is an application problem, and we're only interested in time t greater than 0. So I can ignore the negative square root. That doesn't make sense in the context of the problem, so we're just going to consider the principal square root of the positive one. And then when I grip and rip it on my calculator, they've asked me to approximate it to 2 decimal places. I get 7.56 seconds. So that's the answer to part A. And most of you should have, I hope that you could have done that one without my help. Now let's talk about part B. Part B is the tricky one. In fact, part B is what makes this problem what I like to call a 4-pepper problem. Okay, the part B is what really makes this one tricky. In fact, it's muy caliente, so be careful. Okay, so we gotta find the velocity when the wrench impacts the ground. Well, we know the time of impact is 7.56. So that's our impact time. So we just need to find the velocity at that time t equals 7.56. Well, we're given that the velocity is equal to this limit. Okay, the velocity at time t equals a is given by the following. So the velocity, so we are given the velocity at time t equals a as a limit. It's the limit of the position at time a minus the position at time t divided by a minus t. And we're looking at that limit as t approaches a. Okay, so let's see if we can make sense of this. Well, for starters, let's just look at this expression right here. Okay? Well, the position at time A, and what we're interested in is that 7.56. So actually, let me rewrite this as the velocity at time t was 7.56 is equal to the limit as t approaches 7.56 of s of 7.56 minus s of t, all divided by 7.56 minus t. Okay, so let's start by just, we're going to ignore, let's ignore this line up here. I'm not going to look at that in any more detail than I already did, and we'll go with this new one. Okay, so let's substitute in what we know. Well, the position at t equals 7.56, that's 0 because that's the impact time. So this is 0. S of t is that quadratic function, negative 14t squared plus 800. And then down here in my denominator, I have 7.56 minus t. So let's go ahead and rewrite this. So this is now the limit as t approaches 7.56 of 0 minus negative 14t squared plus 800, all divided by 7.56 minus t. So let's simplify this a little more if we can. The velocity at t equals 7.56 is equal to our limit as t approaches 7.56. So now I'm just going to simplify this. It's 0 minus negative 14t squared plus 800, so 0 minus that quantity. So my sign's basically flipping here. That becomes 14t squared minus 800 divided by 7.56 minus t. And at this point, you should be concerned. Okay, you should be very, very concerned at this point, because if I directly plug in 7.56, then I'm going to get a 0 in my denominator. In fact, let's just take a look at what happens if we plug in 7.56 to the numerator. So I have 14 times 7.56 squared minus 800. And that's a really tiny number. That's essentially going to be 0, because remember this 7.56 number, we rounded that value to 2 decimal places. There were more decimals there. So this, compared to that magnitude of 800, is very, very small. So we basically have 0 divided by 0. And remember, 0 divided by 0 is indeterminate form. We cannot determine the limit from that form. So I got to do a little more algebra right here. And I'll tell you, this is the tricky part for what I think you guys might not think is intuitively obvious. So I'm going to continue with my limit statement here, and then I'm going to start and I'm going to factor out a 14. Well, I don't know what 800 divided by 14 is, so in this case, I'm just going to approximate that on my calculator. Well, I won't do that. I'm just going to write it as 800 divided by 14. We'll throw in decimals here in a minute. Okay, and then I still have to divide that by 7.56 minus t. And this is the step where you might be like, holy cow, does he expect me to come up with this? Take a look at this. This is t squared minus something. So that is basically a difference between perfect squares. Okay, so that's a difference between perfect squares. And I'm going to do a little more simplification here. Okay, so there's my numerator. I just took what the perfect square would be of 800 over 814ths, and it's just going to be the square root of 814ths. But hey, that number looks really familiar. And that 800 over 14 is about 7.56. Square root of 800 over 14 is about 7.56. So we might be lucky here. In fact, I'm going to rewrite now this denominator number right here, that's 7.56, as the square root of 800 over 14. So I'm kind of going back and forth between decimals and exact values here. Hopefully you're able to keep up. But 7.56, so that's 800 over 14 square root minus t. Oh, darn it. I was hoping that that would cancel with something in the numerator, and it doesn't, unless I do another trick. And here's the trick. What I'm going to do is I'm going to write that as the opposite of t minus the square root of 814. Folks, you should be very disturbed by what I just did because I forgot to write my limit statement here. So hopefully I can take that stuff, move it a little bit, and then write my limit statement. Okay, so by factoring out a negative there, the t becomes positive and the square root of 800 over 14 becomes negative. And this, folks, is where the magic happens, because now I have a term that cancels in both the numerator and denominator, and I actually have something where I can try direct substitution again. So this limit is going to be equal to 14 times, well, t is approaching 7.56. Remember that 7.56 is the square root of 800 over 14. So I'm just going to rewrite it as that, plus that same value, square root of 800 over 14. And that's all divided by -1. So let's see what we got here. I have the square root of 800 times the square root of 800. Oh, I'm sorry, those are added. I can't multiply. So I have 14 out here, and then I have 2 times the square root of 800 over 14, because that value is added to itself. I divide that by -1. That gives me the following. I have 14 times 2, that's 28. I'm dividing by -1, so I'm just going to throw that negative sign up there. And then I have the square root of 800 over 14. And now the problem in WebAssign wants an approximate value, so let's go ahead and go back to the calculator. So I have -28 times square root of 800 divided by 14. Some of you will not necessarily know this, but I have my calculator set up to give me an exact value. So if I do this right now, it's going to try to simplify this radical expression. By throwing a decimal point in there, it'll give me an approximate value. And there's my answer, -211.66. And that's going to be in feet per second. Those were the units of the problem. WebAssign asked to round to the nearest whole number. So we're going to just tell it -212 feet per second. And that's the final answer for part B. And yeah, that was a 4-pepper problem, I'm not going to lie. Tricky stuff there. A lot of algebra to get that limit to work. I want to show you this, though. This is a graph of the position function. So we had that -14 t squared plus 800. So this is my vertical position. And you can see that that is decreasing. Now you might be saying, but wait a minute, the graph is a parabola. Well, I know the graph is a parabola, but the wrench is dropping straight down. This is just its position at different times. So out here at t equals 7.56, that's this point right here on the right-hand side. That's our 0, if you will. That's when the wrench hits the ground. Now, let's talk about the velocity, actually. So think about when you drop something. As soon as you drop it, it like starts at 0 miles per hour or feet per second, and then it gradually goes faster and faster and faster. So I kind of want to illustrate what that looks like on this graph. So when you start it, it has a very shallow rate of change. But then as time increases, you'll notice that the slope lines on this graph get steeper and steeper and steeper. In fact, this is a little intro to some particle motion problems we're going to do later. You notice that the rate of change, or the steepness of those little line segments I drew, is getting steeper and steeper and steeper. That is basically physics, and calculus is a tool that was invented to solve physics problems. So we're going to get into a lot more of that as time goes on. Anyway, I hope you find this video helpful.